Now we are looking at how to find the antiderivative of a power series. So let's write our power series a n x minus c to the power of n, so center at c, infinite sum from 0 to infinity, and we want to find what is the antiderivative of this with respect to x. As in the case of the derivative, I'm not going to prove this, but this is going to be the power series that has the antiderivatives of each term. So we're going to have the infinite sum, and then we need to find what is the antiderivative of an times x minus c to the power of n with respect to x. We can take the constant an out from our integral, so from 0 to infinity an, and we need to find the antiderivative of x minus c to the power of n with respect to x. This is going to give us, again I write the same sum, we are going to have x minus c to the power of n plus 1 divided by n plus 1, plus eventually a constant because, well, it's an antiderivative, so there is an infinite family of solutions. So in some cases we may need to find what that constant is if we have some additional information. What can we say about the interval of the radius of convergence? Well, again, the radius of convergence is going to be the same as the original series. So let's write here, radius of convergence, same as the original one we have. Let me copy, so go faster. Yeah. And about the interval of convergence, we need to check the endpoints. Let's solve an example together. It is given that the Maclaurin series for the function 1 divided by 1 plus x is the one I wrote over here, and it has interval of convergence absolute value of x less than 1. We're not proving this here because you are doing it in your assignment. We want to use this to find the Maclaurin series for the function h of x equals logarithm of 1 plus x. And we want to find also the interval of convergence. So let's see this. What do we know? Well, we know that if we consider an antiderivative of 1 over 1 plus x dx, that's our function logarithm of 1 plus x. Well, it could be that plus a constant, but we know that it's an antiderivative. So we are going to apply what we just did. So we are going to find the antiderivative of the series given to us as the Maclaurin series for the function 1 over 1 plus x. So I'll write it over here. So we are going to have the sum from 0 to infinity, and we're going to have a factor of negative 1 to the power of n, and then we are going to have the antiderivative of x to the power of n, so x to the power of n plus 1 over over n plus 1 plus eventually a constant. Let's look at the value of the constant. Let's consider the case where x is equal to 0, so that's where we are centering our power series. In this case, we're going to have the logarithm of 1 plus 0, so the logarithm of 1, the natural logarithm of 1 is 0. On the other hand, we are going to be evaluating our power series where it's centered, so actually we don't need to write all of it. We know that the only thing that survives in that case is when n is equal to 0, so negative 1 to the power of 0, and then we have 0 to the power of 1 over 1, and this is just 0. So that means that the constant c has to be 0 as well. So for our function, the natural logarithm of 1 plus x, we found the associated power series summing from 0 to infinity, negative 1 to the power of n, x to the power of n plus 1, all of this divided by n plus 1. We know that the radius of convergence has to be still 1, so we know that it converges between -1 and 1. And we need to check what is happening exactly at the end points. So we need to check the cases x equals -1 and x equals 1. Let's see what happens when x is exactly 1. So then we are going to have the sum from 0 to infinity, and we're going to have -1 to the power of n, and then 1 to the power of n plus 1, so just 1 over n plus 1. This is the alternating harmonic, starting one step further, and with the sign change, that doesn't really matter. What we can see is that by alternating series test, we'll see right here what we need to check. It converges. Let's see what we need to check. An will be 1 over n plus 1, which is always positive. The an's approach 0 as n approaches infinity, and they are decreasing because n plus 1 is increasing. And so here are the conditions for the alternating series test. So at the point x equals 1, it converges. This is 1 here. That's right. Yes, it converges. Now we need to check when x is equal to -1. In this case, in the sum, we are going to have -1 to the power of n, and then again, -1 to the power of n plus 1, and all of this divided n plus 1. So here we have, let's see what's going on with the signs. We are having -1 to the power of 2n plus 1 over n plus 1. That's, well, sum from 0 to infinity. -1 to the power of 2n, that's just 1, so -1 to the power of 1, so we can just write that 1 outside, negative outside, and we have 1 over n plus 1, and this is the, well, minus the harmonic, but by harmonic diverging, this one diverges as well. So our answer is at -1, it diverges. So let's here use a box to underline this. That's a power series we found, and we also found the interval of convergence. It's between -1 and 1. It is not including -1, and it is including 1. So we saw in this case how the interval of convergence from the original power series changed, because in our original power series 1 over 1 plus x, the endpoints were none of them included, and now that we consider the antiderivative, we included one of the endpoints. So we have to check the endpoints always because the interval of convergence can change.